This video will introduce you to function inverses. Inverse of a function is another function where all x's become y's and all y's become x's. So let's say we have a function that is given as three ordered pairs. The first x is 2 and the first y is 15. The second x is 3 and the second y is 20. And the third x is 4 and the third y is 7. Using the definition of function inverse, we can easily give the inverse of this function. 15, 2, 20, 3, and 7, 4. All I did was I took every x, the 2, the 3, and the 4 in the original function and turned them into y's, the 2, the 3, and the 4 in function inverse. And all the y's, 15, 27, became the x's in the function inverse. And that's what my next statement here says. To find the inverse, we're switching x's and y's and x's. To check if two given functions f of x and g of x are inverses, we have to find two compositions. The first composition is f of g of x, and the second composition is g of f of x. Once you find each of the two compositions, you need to make sure that each one of those is equal to x. F of g of x has to be x, and g of f of x also has to be x. If this is the case, then f and g are inverses of each other. Only functions that are one-to-one have inverses. The functions are one-to-one if they have no repeated x's or repeated y's. Their graphs will pass the horizontal line test. Let's look at the function I have on the top, where my x's are 2, 3, and 4, and my y's are 15, 20, and 7. As you notice, I have no repeated x's, they're all different, and I have no repeated y's. This is why this function that I have on top is one-to-one, and that's why I was able to give it the inverse of it. Well, let's look at the function that will not be one-to-one. Let's say I have 2, 15, 3, 20, 4, 20. While all the x's are different, and this is a function, this function is not one-to-one because the two y's are repeated. The reason for this is the following. If you try to find the inverse of this function and switch x's and y's, you will get 15, 2, 20, 3, and 20, 4. And because of these two repeated x's now that have different y's, the inverse turns out to not be a function. The graphs of two functions that are inverses of each other are symmetrical with respect to the line y equals x. The line y equals x is really just a line that has the y-intercept of 0 and the slope of 1 over 1. So let me draw a function. It's just some random function. I'm going to give it 2 points, -2, 0, and 0, 4. And I'm going to connect the two. Let's say they connect this way. And I would like to draw the inverse of that red graph. Well, first of all, we need to decide if this red graph represents a one-to-one function, because we know that if it's not one-to-one, then it won't have an inverse. One-to-one functions have no repeated x's, no repeated y's, and their graphs pass the horizontal line test. But what does that mean? Horizontal line test checks if any horizontal line that you draw through the given graph will only hit your graph at one point. And as you notice, all of my green horizontal lines only hit my red graph at one point. That's why my red graph is one-to-one function and will have the inverse. Now, how to graph the inverse? Well, we're going to go back to the definition of function inverse, which tells us to simply take all the x's and make them y's and vice versa. So I'm going to do that with the 2 points from my red graph. The first point that has coordinates -2, 0 will become a new point in the inverse of a function where the new x is 0 and the new y is -2. 0, -2 is the point right here. Now the second point that currently has coordinates 0, 4 will have new coordinates of 4, 0, and that's right here. So we'll connect the two, and as you can see, they are symmetrical with respect to this dashed diagonal blue line, and that's how you graph the inverse.